everyone. Are we good on sound? Okay. It works. There we go.
I'm gonna full screen this, all right?
So today, actually, we want to cover a lot of different things. So we're going to move fairly quickly, but hopefully there'll be time at the end for questions. But really, what we want to do today is kind of two things. So firstly, talk about who we are and what we do as an organization. But then the second is that really the best way to tell you a little bit about what we do is to share one of our current projects. So we'll actually be spending the bulk of our time talking about a project with one of our 2017 grant recipients where we were partnering with them to use deep learning to detect illegal deforestation. So I think that will be a lot of fun, but to start a little talking just about us, so I'll let Sean introduce himself, and actually Sean will be jumping in later in the presentation to talk a little bit about the focus of his research within our collaboration with Rainforest. But my background is I'm the executive, wow, that sounded very proper as soon as I said executive. I'm the executive director at Delta Analytics, which is a nonprofit I'll give you some more context on in a little while. For the last 2 years, I have been working at Udemy, which is an online learning company. As part of our data science team, my specific focus has been recommendation algorithms within the engineering org. I am now very pleasantly on sabbatical for 2 months. I leave on Sunday to Nairobi to teach an introduction to machine learning course at some local engineering schools. And then when I come back, I'm actually starting a new position in deep learning research. So that's a little bit about kind of my mix of experiences. Sean, do you want to introduce yourself when you do your section? Oh, okay. Whatever you prefer. So let's dive in. Delta Analytics, our mission is actually fairly simple. It's really, we want to partner data scientists, software engineers, analysts, economists with nonprofits to help them leverage their data to serve their communities. I started Delta Analytics in some ways because of my own background. I grew up in Southern Africa, in Mozambique, South Africa, Lesotho. My family now lives in Kenya. My parents are hippies. And I think that one of the interesting things is, probably similar to your own workplaces, what amazed me when I worked in the private sector was just the divide between that and the nonprofit organizations that they were working for. And I think that we have this amazing concentration of resources and technical skill and outlook in the private sector. And so I think that's why I kind of wanted to start off by really there's an acute need for this type of movement. And I think the best example is that all of us in this room, all these years of technical experience right here, there's probably few rooms in the world that can compete right now. And if you think more broader, there's few cities in the world that have the type of concentration of coding ability, data science, knowledge, and the ability to implement algorithms to leverage data. But at the same time, we have this huge opportunity to finally address these problems that were previously impossible, which makes it really exciting to be involved in this movement. Yes, I do think that one of the big privileges of what we do is that nonprofits care even more. Essentially, they're the people who have decided to work in these communities to make this their life's work, so they're deeply invested in making sure that it makes an impact and they hold themselves highly accountable. I do want to kind of broaden out a little bit. So there's so many organizations that do this type of work, but I'll tell you a little bit about Delta. Our impact. So we started Delta 3.5 years ago. We've done 27 projects so far. We have a community of about just over 90 data scientists, software engineers, and we don't charge anything for our services. So the type of projects that we do are all over the place. Really, the criteria is that your question is interesting and you have data, which actually is fairly restrictive as a criteria because not many nonprofits most of them are thinking about how to collect data and have not sustained data collection over a given period of time. Where do our fellows work? A bunch of places. But this kind of brings me to the group. So we have like every 2 parallel programs. So one is our Delta Data Fellows, and these are really professionals. Everyone is working full time, and then they're giving time outside of work for a 6-month period. So we have like 30 data fellows working alongside a nonprofit. And then we have teaching fellows, and there the mission is different. The mission is really to make machine learning accessible and build technical capacity around the world. And the mission is that we want to empower diverse voices in machine learning and also enable more transparency and accountability to come to the table by doing so, and also allow people to own their data within their communities. So that's a really exciting initiative, and actually this is partly what I'll be doing for the next 2 months, along with a fantastic group of other data scientists, is teaching at a few local engineering schools in Nairobi, but also bringing that back and teaching locally in the Bay Area, but also across the US. So our 2017 grant recipients. Okay, I think I did that fairly quickly. So I think that's good, because I really, we're gonna have plenty of time to dive into Rainforest Connection. So 2017 grant recipients, these are the nonprofits we work with. The one nonprofit we'll be talking about today is Rainforest Connection. And so we also have a mix of other fantastic nonprofits, Build and City Year, both education focused, social justice collaborative. They do very discounted legal services for people who don't have the financial capacity to pay. We're doing like a pricing system for them. But what Sean and I will be talking about today is our work with Rainforest Connection, really fantastic nonprofit. And I think very important to mention is that there's a team of 4, and Sean and I are here today, but Cassandra and Stephen are not, but you will hear probably their names come up as we go through what we've done. And then we're also really collaborating with Christopher and Stefan, and they are the engineers in Rainforest Connection, so this is kind of the whole team. And they're actually in Germany right now, so we really collaborate closely with them in thinking about the problem. So Rainforest Connection has this incredible mission, and the mission is to stop illegal deforestation around the world. And the way that it's solving that mission is by taking recycled cell phones, placing them in the rainforest, and streaming audio 24 hours a day, 7 days a week. So an incredible amount of data. And what is applied to that audio is a deep learning model that will detect the sound of a chainsaw, and upon a positive identification of a chainsaw, send an alert to conservation partners within minutes, who then are able to respond to the threat of deforestation. And within this kind of what I just described, there are so many fascinating problems that really cut to really interesting questions in machine learning. And so I'm going to try and touch on them a little bit here and there today, but things like ground truth, very ominous, but things like having limited label data, and then the different data distributions at each of the different rainforest sites. And so I'll go through that today, but just to give more overview, so there's 3 rainforest sites in Ecuador, Brazil, and Peru, and at each of these sites, we have this thing that are called guardians. And so these are the recycled cell phones. So they're protected from the elements using a kind of a waterproof box. And then they're powered by solar power, and they sit on these canopies above the rainforest. And so the maintenance is low once they're deployed, but it has to be within network range because they rely on local network service. And so that gives us kind of a really valuable data set. And so once the model is deployed and it's scoring the test site, conservationists have access to not only like an alert that was sent to them, but to aggregate information about patterns in general in their region or across the world. Okay. So today we're going to be talking about the 3 goals of this project. And so the 3 goals are, firstly, delivering as accurate a model as possible and having the conservation partners trust when they're getting an alert. The second is really building our engineering capacity. So we're not going to talk about that today, but Stephen just finished a fantastic modeling pipeline, and the whole goal is to have flexibility and API calls to make it a repeatable process and to also allow for feature engineering. It's really fantastic, and we're going to be opening up that code to the rest of the research community probably in around July on our GitHub. And then the third piece, which Sean is going to take over, and it's really a fascinating piece of research, is how do we not only identify a chainsaw, but also tell conservationists where it's coming from. Because actually, it turns out it's very painful to trek through a mile of rainforest. So really, the triangulation of sound is a fascinating problem in this particular context, and Sean will lead it through. So what is our training data? This is where it starts to get interesting, because we actually have very little labeled data. And so our training data, the bulk of it is from kind of experiments / opportunistic grabs of data. So for example, Sean's parents had a tree cutting at their house, and we were there with the guardians to set up and get clean labeled data. And again, we have a Berkeley site, and we have another local site. And so really that is the bulk of the label data, because initially, especially at the test sites, there was very little label data. And so then we're augmenting that with pseudo-labeling. So we're taking the trained model and we're applying it to the test site, and then we're identifying positive cases, and then we're doing a human kind of validation of whether it's actually a chainsaw, and then adding that back into the training set. Just even with this additional step of pseudo-labeling, we do have this big problem of limited labeled training set, which will come up again. And so and the approach is that we're treating an audio recognition problem as an image recognition problem, and we're applying a deep learning model. And I think it's interesting to pause here and kind of think about why this is an appropriate tool for this task. And firstly, I acknowledge that there's been a lot of interesting research around applying deep learning models to audio. So for example, the first real paper on applying deep learning models to spectrograms, which we will talk about, and I'll give you some additional detail, was in 2009, and it came out of Stanford. So that's actually fairly recent. And then last year there was a fascinating paper, that the WaveNet paper, which is talking about generative models for producing audio. And so we have this enormous quantity of research around firstly treating audio classification as an image problem, but then also using even raw audio now as an input into deep learning models. And so why is it an appropriate tool? It's because there's a natural hierarchy to sound. So if you think about frequency or pitch, and if you think about if you think about the time element of sound, so the tempo, the amplitude, really those provide a natural hierarchy that deep learning models are excellent at representing. And so you then have this really powerful way of extracting meaning from your unstructured data. And in particular, even for our specific narrow use case of a binary classification problem, it's incredibly powerful. So I'll provide some context. Some of you may not have background in signal processing. So we actually, before I describe a spectrogram, we're applying a convolutional neural network to this problem. And a convolutional neural network is really, you're making the assumption that the input is an image of some kind. And because of that, you're able to embody kind of features in the architecture that save you from using a lot of parameters. It basically is a very efficient way of training a model. And I do want to mention here that it's actually a little different from your typical image recognition problem, because your typical image recognition problem, you have spatial features. But here, by using a spectrogram, you actually have a relationship between frequency and time. So it kind of creates these interesting kind of implications of what features you're extracting. Because, for example, if you had a square window, then you're treating frequency and time equally, and you're extracting features from both. But if you have a 1 times n window, you're extracting features from your time features, essentially. Things like tempo, things like rhythm. And if you do an n times 1, you're extracting frequency features. So it's a little different, but it's really kind of powerful at capturing a lot of the dynamics of audio. And just a little bit of background. So a spectrogram is a way of capturing features of sound, namely amplitude, frequency, and time. So if you look at this, this is just an example of a spectrogram of one of the, I believe this is a chainsaw, possibly. So on the x-axis you have time, on the y-axis you have your frequency, which is the pitch of sound, and then the color spectrum is getting at your amplitude, which is really like the how noisy the sound is. And so this is what we're feeding in as an input into our convolutional neural network. Oh, so I don't kind of know how to do this on this thing. I do have links to actual audio files, but this is basically getting at kind of something I really do want to get across, because I think it's such a meaty research question, is that not only do we have limited labeled data, but within that labeled data, we actually have very clear cases of a chainsaw, which is the bottom spectrogram, and we have I think it's interesting to listen to it, because all you really hear is a bird, and then towards the end you have this slight background noise. And it's almost, I don't know if many of you may have experience in fraud detection, but it kind of gets the idea of classification at the edges is very easy, but it's the shades of gray that are very difficult to give the model enough examples to understand and be able to correctly classify. And so this is just another kind of moment to pause and think about our inputs. So this is a comparison of the spectrogram for a bird noise, and then at the bottom, I don't know which is at the bottom from here, but so it's comparing a bird to a chainsaw, and what you can see, so this is also why this is a fun machine learning problem, because yes, these are different, but they're barely perceptibly different. Like if I had to look at a ton of these, to the human eye, it's not like a stark contrast, but it's perfect for a machine learning application because it's a nuanced difference. And so it's really kind of a beautiful example of how we should be applying this type of technology. So yeah, just a little more detail. So essentially we're treating this like a binary classification problem. So our loss function here is a cross entropy loss. We're using the softmax classifier. So basically we have multiple hidden layers. And then at the very end, we have a logistic regression. And so all that's doing is squashing our 2 neurons that are in the final layer into a range between 0 and 1, and we can treat that like the distribution of probabilities. So it's very intuitive as an output. We can basically say, oh, it's 0.7, so 70% chance that it is X and 30% that it is Y. And kind of similar to all shared features, all shared characteristics of neural network architectures, we have a nonlinear activation, we have hidden layers, and then we have a training. And in this case, it's backpropagation. So meaning that we are almost learning by mistake. So setting our weights and then updating the weights in order to reduce our target loss function. The architecture that we found worked well. We did variations on it, but it's actually very well-known architecture. So it's the AlexNet architecture, which was originally trained on ImageNet, which is a fantastic data set of 15 million images with, I I believe, over 10,000 classes, but really it has probably very, very few hidden layers, and it has the three characteristics of convolutional neural nets. So it has a convolutional layer, max pooling layer, and then it has a fully connected layer. So I'm sorry if this might be, I always sense these talks that it's fun to go over kind of a mix of like new, but also that steady rhythm of things you already know. But I think that moving past that, let's talk about the new and the interesting elements posed by this particular problem. So, 3 minutes till the end? Wow, okay, I'm gonna switch over to Sean. Okay, Sean, you go for it.
Okay, so as Sarah was going to talk about, we've done a lot of research, a lot of work on improving the classification engine, and so that's kind of been the main scope of what we've been doing. A more research-based topic that I've been working on actually is, get to it. Actually, I'll talk to this really quick. So one of the methods we've been applying for improving the classification model is independent component analysis. And the reason we're looking at this is because neural network is great at detecting structure in images. And with our samples, we have the chainsaw component, and it's combined with the background noise you find in a rainforest. And this muddies any structure that you do have in the actual chainsaw image. So kind of the research area that we're looking at is being able to, on known positive examples, we're gonna look at training a ICA model. And then once we've done that, the ICA model should be able to detect chainsaw component versus the background noise component. And once we've trained that model, we're gonna actually just apply that to the samples. And hopefully we'll get any chainsaw component in the sample, whether or not it's a positive or negative sample, and any noise component. And we're proceeding down this path, and kind of what we're working on now is we know we have the ability to detect or extract multiple components, and working this into our model. Do we use both components? Do we use just the chainsaw component? We're still kind of researching that area. And in just 2 minutes, I'll go over the research area that I'm focusing on, and that's modeling the direction and distance estimation. The reason this is so important to the rainforest, and Sarah kind of touched on it, is the sensitivity of the guardians. They're able to detect sound within 1 square mile, and I don't know if you've been to the rainforest, but searching 1 square mile takes forever. So if we can give, along with the alerts, we can get some estimation of direction and distance, that will greatly help the rangers that are going out and investigating these alerts. So working with Rainforest Connection, we've been given our own test site. We have our own guardians, so we can create these experiments. And the approach we're going to be using is sound localization based on time delay of arrival. And this is a pretty standard technique, but I just want to hint at, I won't go over the details on it. Given our setup, we have some very unique challenges, and some of these are, most times when you're doing source localization, you know the position of the sensors. In this case, because as you can see in the picture, the guardians are placed in the tree kind of wherever it's convenient. So in that sense, we don't know where the guardians are located. Another thing that we've kind of been grappling with is the guardians lose sync both in time and they drop samples. So we're having to come up with algorithms that are robust to deal with missing data. And the other piece is this large coverage area. They want to be able to apply as few number of guardians and cover as much of the rainforest as possible. And that's kind of a trade-off between accuracy of your direction and distance estimations and just the number of guardians that you're placing in the forest. So go on to our next steps. We're going to be delivering the cohort for this year ends in July, so we're going to be delivering our final project and giving a poster session at the University of San Francisco, delivering the results. We're going to be, as Sarah mentioned, packaging up our code and giving it to as a resource to researchers, and we're looking to potentially publish the research paper on estimating directionality. And finally, if you guys are interested in the data for good, we're getting ready at Delta Analytics. Starting in July, we'll be recruiting fellows for 2018. So if you're in the Bay Area and you're interested in doing data for good, feel free to check out the website and potentially join us next year. Thank you. Any questions? Question? Yeah. That's actually a good question.
Well, actually, it's, I want Sean to answer that.
No, so
well, we did have the audio set.
yeah, one of the things that, in part of building a more robust model is using additional features. And so like one of the things that we're looking at is, the combination of a vehicle alert combined with a chainsaw alert and then adding, the falling of the tree. That could be, give you more confidence in your detection. So yeah, that's a great example of, this additional data that you can do to just increase your confidence in your estimation.
I'm just curious if most of the fellows get support from their employers on their own sabbatical, or that's not.
So actually, this sabbatical is just because of my unique circumstances. So I am starting a new position in July, and I was able to carve out 2 months to do something that I've wanted to do for a long time. But all of our fellows work full time, so everything is based around these little groups of 4 professionals, and it's a combination of monthly hackathons, and then you're meeting with your groups. So yeah.
Is there any daily or seasonal changes to the background noise?
Yes, there is. So actually that kind of gets to one of the other difficulties of the difference between our training, basically our test accuracy within our label data, and then the difficulty in actually deploying to the test site. So for example, hour of day actually matters a lot at the test site because illegal deforesters tend not to go into the forest in the middle of the night. But then to your point of seasonality, that also matters because rain tends to introduce a lot of background noise that affects the ability of the model to detect, but also rain probably makes it less likely that there's deforesters in the forest. So introducing more examples of that background noise is really imperative for the model to be able to adapt to the different test conditions. That's one of the steps we're doing right now by augmenting the data set with the audio set data that was just released by Google. And it will include sounds of rain, sounds of trees falling, sounds of wind, and other environmental factors that tend to throw, in particular, on negative class, because in some ways the negative class is just as important. We need to give enough examples of what is not chainsaw in different environmental conditions in order for it to be able to handle the difference in data distribution at different times of the year.